Okay, good afternoon. Now, today we will see remaining part of this measurement of sound and vibration. In that, we will study only microphones. Microphones are transducers to convert sound pressure variation into the analogous electrical signals. The main factors in the selection of a microphone as sensitivity, frequency response, dynamic range, and linearity. Microphones generally employ a thin diaphragm to convert pressure into motion. The motion is then converted into a suitable electrical output by employing a secondary transducer, which may be either of the following. First, condenser or capacitor type microphone. Second, electret microphone. Third, piezoelectric microphone. Fourth, electrodynamic type microphone. Now we'll see the microphones one by one. First is condenser or capacitor type microphone. Therefore, this is the diagram of the condenser and capacitor type of microphone. See that capacitor means what? Two parallel plates are there. Therefore, same thing is here. This is one thin diaphragm is there, and parallel to this, another this. Another this construction is there, and this is also acting as one plate. Now, in this housing, these holes are provided for the damping or air circulation. Now we'll see the its working. The capacitor or condenser type microphone is most widely used for precision measurements because of good frequency response, excellent linearity, and large dynamic pressure range. A typical construction of this type of microphone is shown in figure. The microphone cartridge consists of thin metallic diaphragm in close proximity to a rigid back plate. The diaphragm and the back plate form the plates of the capacitor. The movement of the diaphragm caused by the impingement of sound pressure results in an output voltage given by E is equal to QD, where E is equal to output voltage of the capacitor, Q is equal to charge provided by the polarizing voltage, D is equal to separation of the plates. Therefore, see that this is the construction. This is the thin diaphragm. This is the back plate. It is holes are provided for the damping. This is the insulator. This is the microphone housing. Now the air gap between this diaphragm and this housing is 0.002 centimeter. This is the protective layer. Now this in the housing, this hole is provided for air leak capillary for static pressure equalization. On both sides, pressure should be equal. That's why these holes are provided. The microphone is provided with a capillary air leak equalization of pressure on both sides of the diaphragm to prevent the diaphragm from bursting. Further, the back plate, this is the back plate of the condenser microphone, is provided with damping holes. The motion of the diaphragm causes airflow through the holes, which results in energy dissipation because of fluid friction. This damping effect is utilized in the control of resonant peaks of diaphragm response. These microphones have good accuracy or good frequency response even at high frequencies, and also have good acoustic sensitivity. However, they are susceptible to errors caused by humidity, which reduces excessive background noise due to the leakage of the charge. Now next is the electret microphone. Electret condenser microphone is an improved version of ordinary condenser microphone. In the condenser microphone, we need to supply a depolarizing voltage, whereas in electret microphone, the polarized element, namely the thin coating of the electret material, supplies the bonded charge to the backplate of the electret microphone. In other words, it is a self-polarizing type of condenser microphone. The principle of operation of the electret microphone shown in figure is precisely the same as that of the conventional condenser microphone. They have excellent frequency response and are relatively free from noise in humid environments. However, the aging of the electret material can cause errors of the order of 0.2 dB per year. This is the electret microphone. Here, thin coating of electret material on the back plate. This is the back plate. Again, same construction is there. Next is piezoelectric crystal type microphone. Certain materials possesses the ability to generate an electrical potential when subjected to mechanical strain. Such materials are generally crystalline in nature and are known as piezoelectric crystals. The commonly employed materials are quartz, Rochelle salts, that is potassium, sodium, tartarate, lead, zinconate, titanate, barium titanate, and ammonium dihydrogen phosphate. Rochelle salt has strongest piezoelectric effect and is widely used as microphone transducer. However, it requires protection from moisture in the air and cannot be used above 50 degrees Celsius. Further, quartz is very stable, but its output is quite low. In practice, lead zirconate titanate (PZT) is commonly used in piezoelectric microphones. The force produced by the acoustic pressure on the diaphragm is used to strain the piezoelectric material, which in turn produces voltage output in direct proportion to the applied force or acoustic pressure. For the greatest sensitivity, a cantilever type of crystal element is mechanically coupled with the sensing diaphragm. Further, other constructions employ direct contact between the diaphragm and the crystal element, either in bending mode or direct mode, that is, element is subjected to direct compression. Piezoelectric microphones are very sensitive and can measure accurately sound pressure levels below 24 dB. Further, their response at lower frequencies is also very good. However, their response at higher frequencies is not as good as condenser microphones. In addition, they require impedance matching and are also sensitive to vibrations. Therefore, this is the piezoelectric type of microphone. This is a piezoelectric material in cantilever type bending mode. Why it is known as cantilever? Because its one end is fixed, the other end is free. This is the other end. This is the conical diaphragm. This is the acoustic pressure. Therefore, when acoustic pressure will act, this conical diaphragm will bend like this, and it will exert force on this piezoelectric material. And you are knowing the characteristic of piezoelectric material, that when piezoelectric material gets distorted, an electrical charge is produced. That's why this electrical connection is there. Next is electrodynamic type of microphone. This type of microphone is based on the principle of generation of EMF when a moving conductor is placed in a magnetic field. Figure 7.10 shows the typical construction of this type of microphones. The sensing diaphragm is attached to a coil or ribbon placed within the poles of a permanent magnet. The movement of the diaphragm due to acoustic pressure generates the analogous induced voltage in the coil. The output voltage V of the electrodynamic microphone is given by V is equal to P into L into U volts, where B is equal to magnetic flux density in Weber per meter square, L is equal to length of the conductor in meter, and U is equal to velocity in meter per second. Such microphones have the advantage of being self-generating, but their frequency response is poor due to the high inertia of the moving coil. Therefore, this is electrodynamic microphone. Why it is known as electrodynamic microphone? Because it consists of two permanent magnet, and in between the permanent magnet this soft iron core is placed, and because of this the movement of the diaphragm due to acoustic pressure generates the analogous induced voltage in the coil. Therefore, if this diaphragm will move, what will happen? The voltage will be induced in the coil, and that it is directly connected through this terminal, and this voltage we will get the record of voltage, and that voltage is directly calibrated in terms of sound or in terms of pressure or sound pressure, and we are getting directly the reading of sound pressure. Therefore, these are the microphone. Therefore, this chapter number 7 has been completed. Now we'll go to chapter number 8. Okay, we'll wait. We'll see here. Presentation. I think this chapter is completed. Therefore, what we'll see tomorrow, we'll see next chapter, that is chapter number 8. Today we'll stop here. Thank you very much.